Okay, good morning everyone. So today we will move to the next transistor that we will focus on, which is bipolar junction transistor. And then normally we just call this as a BJT. So basically as you can see from the name of this transistor is considered as a junction, which means that we should have the several junctions that combine with each other. So that's why we call the junction transistor. But also it's considered as a bipolar. That means that this is the structure that both that involve as a transistor that both involve as a electron hole as a carrier, so which is actually as a structure that combine both of the two kinds of the PN junction together. That we call this as a bipolar junction transistor. So first of all, this is a intended learning outcome for this chapter for the bipolar junction transistor. So first of all, for sure that everyone is expected to understand the operation principle. 什么？13里面好像还没有收。Oh, really? Okay. Let me check the E3s. Okay, so I just upload the slide to the E3 now, so you should be able to access the slide. Okay, so first of all, we will explain the basic operation for BJT. That's very important, especially the BJT is a little bit, the operation principle is pretty different compared to the MOSFET. To be honest, the MOSFET is more easier than the BJT, because of bipolar transistor is considered that we both have to take into account the electron holes. So therefore the carrier injection and diffusion and also the collection mechanism are very important for the BJT. And then for the BJT we have the 4 different operation modes here, which is include the cutoff, forward active, saturation, and inverse active. So these are the 4 different operation modes. And also it's very important to understand the minority carrier distribution and then the transistor currents, especially focus on the forward active region, and also to understand the current gain mechanism. So that's also very important for BJT. And also we need to understand the several non-ideal effects and also the breakdown mechanism. So these are pretty unique for the consideration of the bipolar transistor. But if you're already familiar with the PN junction, then actually the bipolar just considers 2 back-to-back PN junctions that combine with each other. So first of all, we just have to show the structure for the bipolar transistor. So we can consider there are the 2 different kind of the bipolar transistor, junction transistor here. So we have the one where we have the N++ on the left hand side, we have the P+. In the middle, we have the N on the right hand side. So this is typically we consider as a NPN BJT here. And then we consider in the left hand side as a emitter. And then the middle side we call as a base. And then the right hand side we call this as a collector. So that's a three terminals, the name of the three terminals for this BJT, for NPN BJT. So we have the emitter and base and then the collector here. And as you can see from this structure, we consider as two NP junction. One, we have the PN junction here. We have another PN junction here. So therefore, when we analyze the bipolar transistor, we have to focus on the understanding of these junctions here. So which we have, the first one is a base and emitter junction. And then another one is a base and collector junction. So this is a typical structure for the NPN BJT. And normally we can also put as the circuit symbol to represent this BJT, which we have the circuit symbol shown here. So which we have the base here, we have the collector here, we have the emitter here. So this is a circuit symbol that normally you probably already learned from the basic electronics when we introduce the typical circuit operation for BJT. So we will use this as a circuit symbol to represent as a NPN BJT. And similarly, we can also have the PNP BJT, which is shown on the right hand side. So the structure is exactly the same. From the left to the right, we have the PNP here. So on the left side, we have the P++. In the middle, we have the N+. And on the right, we have the P here. So similarly, we call this as an emitter. And then in the middle, we call as a base. And on the right hand side, we call this as a collector. So if you look at the circuit symbol for this PNP, which is shown in here, so still we have the base here, but now we have a collector and then emitter, but now the arrow is in this direction. So that's a circuit symbol for the PNP transistor here. So, and then also the understanding of the or analysis of this PNP BJT is highly related to the characteristic between this junction. So these junctions are also very critical that we need to understand when we try to analyze, no matter for the NPN or PNP. So basically, the bipolar junction transistor is a three-terminal device, similar to the MOSFET, but now we have the emitter, base, and collector here. And we have the two different junctions that we have to be care of, which is a base emitter junction and also the base collector junctions here. So these are the two most critical junctions that later will have highly influence for our carrier transport. So, if we look at the concentration, the net concentration from the left to the right, so we can plot as shown here, which is ND minus NA, and normally we will design our BJT as N plus plus in the emitter region, as a P plus in the base region, and also the N in the collector region, where we will explain later that this kind of design is critical for our bipolar junction transistor. So when we consider the bipolar transistor action that we have to take into account as the different forward and reverse under the different PN junction. So as shown here, this is a base, this is a collector, this is emitter. So we have to apply the bias we consider as 4 different quadrants operations. Where we have the VCB, which is a collector, the voltage between the collector and base, and also the VBE, this is the voltage between the base and emitter. So therefore we have to consider the bias between this PN junction, whether we can either have the forward and reverse, or the bias between this junction where we can have the forward and reverse as well. So the first one is that if we consider the operation in the first quadrant here, which is VCB is a positive and VBE is a positive, and in this consideration where we call as a forward active, which we forward bias between the base and emitter, but reverse bias between the base and collector. So that's the operation region where we consider as a forward active, where we have a forward bias in this base emitter, but the reverse bias between the base and collector. So basically, with this consideration, we can have the 4 different quadrants operation. Just either depends on you forward or reverse PN, or forward or reverse between this junction. So therefore, if we do the BE reverse bias, BC reverse bias, where we call this as a cutoff region. And the second one where we have been mentioned, the forward active. And the third one is BE as a forward bias and BC as a forward bias. And this is the one we call the saturation. And the last one is the BE under the reverse bias and the BC under the forward bias. So this is the region we call as the inverse active. So the operation of the BJT just very simply depends on how do we bias between these two back-to-back PN junction as respect to the center point of the base. So that's why in the middle we call as a base. And one more things want to mention that for the BJT, it's very important to understand that we have the base current here, which is very important because of the BJT normally considered as a current drive device. So we need to have this base current to turn on our transistor, our BJT. This is something a little bit different compared to our MOSFET. For MOSFET, we have the voltage as a voltage drive device that we use the gate voltage to turn on of the transistor. But in the BJT, we use the base current to turn on our BJT. So the typical characteristic for the BJT, which is the one we are interested in, is a collector current versus the VCE. So this is a typical IV characteristic that we are interested in, which is IC versus a VCE. And then the typical characteristic is very similar to the MOSFET. We still have this kind of the characteristic. And then the only one of the main difference between the MOSFET and then BJT is that we need to increase the base current as long as we have a higher base current. Then we can have the higher collector current. That's why we consider this as a current drive device, because we need to have the base current here. Although normally we typically draw as a BJT shown in here, where we have the structure as an emitter, base, and collector, but for reality, the device will be fabricated as shown in here, where we have the P base region, collector, and these are all as a emitter terminal. So therefore, each one can be considered as a one BJT here. So we have NPN, we have NPN, 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 and NPN here. So that's how we realistic to fabricate the bipolar junction transistor. So as we already mentioned that when we talk about the PN junction, that we already derive, we spend a lot of efforts in the end to get this conclusion that the current transport in the PN junction, if you still remember that the main conclusion we derive for the PN junction is that the current transport in PN junction is dominated by the minority carriers. This is how we, in the end, to get the current equation in the PN junction. So therefore, if we try to analyze the bipolar junction transistor, we have also need to take into account as a minority carrier. So one of the critical things for to analyze the BJT is we need to understand the minority carrier distribution. So therefore, we need to spend a lot of time to understand how this minority carrier distribution along with two back-to-back PN junction here. The first one we are interested in for sure will be the forward active. So the forward active is a condition that the BE junction is under the forward bias and the BC junction is under reverse bias. So now we just try to combine what we have learned from the PN junction as a minority carrier distribution in the PN junction, but now it's a little bit complicated because now we have the two PN junction back to back with each other. So let's do this drawing step by step. So the first one, from the left to the right, we have an emitter, we have the base, and we have the collector. So since we already knew that from the left to the right, which is N, in here we always use NPN as an example for the illustration because that's more easy for the understanding. So we have the NPN. But as we have been already shown that we will design as a emitter as a N++, and then the base as a P+, and then the collector just as a regular N here. So this is the carrier distribution that for each junction. So first of all, we have to consider that from each junction, in between of each junction, for sure we will have the depletion region in between. So therefore, we will have the depletion width between the emitter and base, and we will have the depletion region between the base and collector here. So now we put as x-axis here, where we have the x equal to 0, and this is the width of the base we call as xb. So therefore, this is x equal to xb, and also we have the x prime equal to 0, and the width of the emitter x prime will be equal to xe here. And similarly, we can have we have to consider the width of the collector, where we have the x prime equal to 0 and x prime prime equal to xc. So now the next step is that we need to first have the equilibrium minority carrier concentration. Since we have the N++, which means the major carrier for the electron here are pretty higher concentration. So now if we try to plot as a minority carrier, which is a hole in the emitter, which will be in this kind of level, which is a P, the whole concentration in the emitter region. And this is a PE0, which is an equilibrium case. And similarly, if you try to consider this is a P+, which has a relative higher whole concentration. So therefore, we will get the minority carrier in the equilibrium case, which is this one. And in this case, the minority carrier is electron. So the N is a minority carrier as an electron in the base region under equilibrium. And then the last one is a N, which means the whole concentration in here as a minority carrier, as shown here, which will be a PC0. The reason that we have these three different levels of a minority carrier concentration is because we have a higher majority carrier concentration in here, right? So if you still remember that the very fundamental equation, the N times P is equal to the Ni squared. So you got a higher concentration of electron, for sure you got low concentration of hole. You got a lower concentration of electron, you got a higher concentration of hole, because the N times P will be always equal to the Ni squared. So that's why we make this whole minority concentration as shown in here. So that's a second step. And then the next one is we just combine that where we have been learned from the NPN junction. That is, the first one is consider this one as a forward bias. The forward bias means that in this case, we will have the P as a whole will be able to travel through this and in the end to reach to the emitter region. And therefore, the concentration at this region for the hole that's coming from the base, which is here. And then as we already derived, if you don't remember, just check how we spend the effort in the PN junction. So we will have the exponential decay as the distance increase. So therefore, we can expect our whole concentration in the emitter region will be shown like here. So therefore, this is a PEX prime. So this is exactly the graph that how we make it once we consider a PN junction under the forward bias. So just let me illustrate again. This junction is under the forward bias, and therefore the holes are able to inject it to reach to the emitter side, which is the N plus region. And once a hole reach to here, will become as a minority carrier, and therefore will follow the same equation that we derived before, that will follow as a exponential decay as a concentration, and therefore you will expect to see this kind of the whole concentration distribution, and in the end to reach to the equilibrium whole concentration PE0 here. So Similarly, if you follow the same idea, this region is under the forward bias, and therefore the electrons are able to inject and travel through to reach to the base region. So therefore, ideally, we should have the electrons here. The electrons at the base region, and that will still follow the same of the exponential decay. So if you remember the previous analysis for p-n junction, we should get the graph something like this one. So that will be in the end to reach to the equilibrium of the minority carrier concentration, which will be the NB0. But the one thing difference between the pure p-n junction versus the bipolar transistor is that we also need to consider this is under the reverse bias, which means that the reverse bias means that the carrier here at this location definitely will be equal to 0. Because this is under the reverse bias. So ideally that we won't have any carriers be able to inject from the base to collector, because this is a reverse bias. So therefore we will force the minority carrier distribution will become 0 at this region, and therefore in the end you will see these distributions. So ideally we should follow the same analysis like the p-n junction, that you have electrons are able to inject it to the base region, and in the end follow the exponential decay to reach to the status, to the equilibrium of the minor carrier concentration, which is NB0. But the difference here is that we have the reverse bias here. So the reverse bias will force the electrons will have to become as a 0 at this point. So therefore you will see this kind of a minority carrier distribution in the base region. So this is a difference between the pure p-n junction and the minority carrier concentration, the electron concentration in the base region. So that's a main difference. I hope you can follow, but if you cannot, just think about this. It's not that difficult. This is just a one thing difference. And then also this is under the reverse bias, which means that the minority carrier concentration, which is whole in here, will be equal to 0 as well. So therefore the starting point here will be equal to 0, and then gradually have reached back to the PC zeros. So that's seems in the collector region. So most of students, including me when I was a student, it's always very difficult to understand why the carrier distribution, why it has to be drawn like in this way. Then in the BJT, that's why that many of us are always very afraid to learn the bipolar junction transistor. But if you have the understanding coming from the p-n junction, I hope that this will not be very difficult for everyone. Just need to take into consider that in this case the base collector is under reverse bias. Since this is under reverse bias, so these 2 points, this concentration at this location must be equal to 0. Okay, So that's for the forward active. Then now we will look at for the saturation. So this is a case under the saturation. So still the same. We are first we know that we have the three different regions. We have the emitter, we have the base, we have the collector region. And then for each junction, first we draw the depletion width between each region. And now we all knew that the minority carrier concentration will be this kind of the level. So therefore we have the PE0 here. We have the NB0. And we have the PC0 here. So under the saturation, the BE is under forward bias. So therefore, the minority carrier distribution in the emitter region will be same as a forward active. So that's a PEX prime here. And right now, the base collector is under the forward bias as well. So therefore, in this case, this is under reverse bias. Now this is under the forward bias, and therefore there's a slightly difference compared to the left hand figure, because right now this is under forward bias, so the holes are able to inject to the base region, but because of the emitter, the electron are able to inject it to the base region. But because of the base collector is under the forward bias, so therefore the electrons are able to go through again from the base to collector as well. So therefore, we will have the NBX, which will have this at this point will not equal to 0 because this is under the forward bias. And then this one will still follow the similar for this PN junction. So we will decay to the PC0 here. So this is a minority carrier distribution on the case with a saturation. So once you are able to understand the minority carrier distribution in the case with forward and saturation, and then the rest of the two will be very similar, just as an opposite consideration. So the first one is a cutoff. So in this case, is base and emitter under reverse bias, and then the base collector is under reverse bias as well. So we have an emitter, base, collector, which is N++, P+, N here. And again, this is a depletion width between the emitter and base, and also between the base and collector. And we draw the static minority carrier concentration. Which is a PE0 and NB0, and also the PC0 here. And because right now the base emitter is under reverse bias, so just have to remember, as long as under reverse bias, the concentration here at this boundary must be equal to 0, and therefore we have this kind of a distribution. And because of the base and collector is also under the reverse bias, so this and this, the concentration here must also equal to 0 here. So therefore we have the distribution like this one. And also similarly we have a distribution like this one. So this is under the cutoff operation. And the last one is under the inverse active, which is just completely opposite compared to the forward active. So still we have an emitter, base, collector, N++, P+, N, and in this case, the BC is under the forward bias. So we start to draw the BC first. This is under the forward bias between these two junctions. So first of all, we will have the minority distribution as shown here. And then again, between the BE junction is under reverse bias. So therefore, the minority carrier concentration must be equal to 0 at these two locations. So therefore, we will have the minority electron distribution as shown here, which is NB respect to the X location. And we have this one, which is a PE, the whole respect to the X prime position. So this is the minority carrier distribution for the inverse active, which just completely opposite compared to the forward active. So now we will try to analyze the actions, the forward active operation actions further. With previous consideration that under the forward active, the base emitter PN junction is forward biased. And then the base collector junction is a reverse biased. So therefore, we can still consider to have the band diagram between these two junctions. So the middle one here, this is under the zero bias. So because we have the NPN here, so therefore under the zero bias, at the emitter you have a Fermi energy which is close to the conduction band. In the base you have a Fermi energy close to the valence band, and then again in the collector you have a Fermi energy close to the conduction band. But now if we consider as a forward active operation, and therefore this junction is under the forward bias. And therefore the barriers between these P and N is reduced. So once the barrier is reduced, the electrons are able to across these barriers. Because the barrier is reduced, so electrons are able to start to across these barriers and start to reach to the collector side. And again, these junctions between the base and collector is under the reverse bias. So therefore, there will be a huge barrier height between these junctions as shown here. So once electrons injected from the emitter to the base, then reach to this region, these electrons are able to be accelerated by this huge barrier drop, which is a high electric field, and that we will explain later. So the next is we need to start to understand the how these carriers moving from the emitter to the base and in the end to reach to the collector size. So the first one, the base emitter PN junction is forward bias. So these are under the forward bias. So electrons from the emitters are injected. So the electrons are injected across the B junction into the base. So this can be understood from this Venn diagram that the electrons are across B junction and injected into the base. So as shown here. So these injected electrons create an excess concentration of the minority carrier in the base, right? So once we have the electrons are injected into the base region, and these additional electrons become excess carriers in this region. So these electrons create excess concentration of a minority carrier in the base, and then the base collector, because of at the same time this is also under the reverse bias. And once this under the reverse bias, the minority carrier electron concentration at the edge of a BC junction is ideally 0. This region, this location, at this location is ideally 0. So therefore, we can start to see the large gradient in the electron concentration. So you have a very high electron concentration at this location, but it will be forced to become 0 at here. So therefore, we create a large electron gradients here. So the large gradient electron concentration means that electron inject from the emitter will diffuse. We have this large concentration gradient that will cause the diffusion. Across the base region. So therefore, we will have the diffusion across the base region and then into the BC space charge region. This is the BC space charge region here. And now, because this is under the reverse bias, and therefore the electron diffused to here will be able to inject it to the collector because of the electric field will sweep the electron into the collector region. So the electron will be accelerated, swept by the electric field in the end to reach to the collector side. This can be also understood from the previous Venn diagram. The previous Venn diagram already mentioned that once the electrons reach to the base collector space charge region, because this is under the reverse bias, so that we will have the high electrical field. So the carriers, the electrons, are being swept by this high electric field, and then in the end to reach to the collector side. So you can either understand from this Venn diagram or from this as well. So these are the always that the in the end can get a very consistent mechanism. So let me illustrate it again. So first of all, this is under the forward bias. The forward bias, the electrons are be able to inject it to the base region. But also this is under the reverse bias. So the concentration at this location will be equally as of 0. And therefore, we will create a large concentration gradient that will cause a diffusion mechanism. So the electron will start to diffuse through the base in the end to reach to the BC space charge region. And this region, this junction is under the reverse bias. And therefore, the electron here will be swept by the electric field in the end to reach the collector side and become as a current here. So that's how these BJTs work. That's how that we in the end we have the carriers from the emitter reach to the base in the end to reach to the collector. But this kind of the concept, this kind of mechanism actually are very similar to what we have learned from the MOSFET. So now I will explain to you that how this operation is very similar to what we know from the MOSFET operations. So in the MOSFET, we have the P substrate here. Then we will have the source and drain. So we have the source as a N plus, drain as a N plus, and then we have the dielectric. And the gate. So if you still remember that the operation for the MOSFET is that on the one terminal we will apply the gate bias, but at the meantime we will apply the drain bias. And the drain will gradually increase. And as the drain increase, we will start to foresee this NP junction is under the reverse bias. Therefore, we will start to see the expanding of this space charge width from this NP junction, right? And what we knew from the MOSFET is that first of all, electrons, why we call the source, because that's a source for the electron. So electron will always starting moving from the source region and gradually moving into the channel region, where as long as we have this higher drain bias and therefore our channel region, the inversion charge in the channel will become as a triangular here. And therefore, the electron will first to diffuse into this channel region. This is the channel regions here. Sorry, I need a little bit mess up this one. So we have the electrons in the source and start to diffuse into the channel region. And in the end, how this electron to reach to the drain side is because of at this junction is under the reverse bias. So therefore, electron will be able to go through this reverse bias region because of due to the electric field. So therefore, due to the same mechanism that swept by the electrical field, and in the end become the drain current to reach the drain side. So therefore, if you try to look these two transistor operation closely, you'll find out that actually the operation mechanism are very similar. In the bottom case, we have the emitter base collector, we have the NPN, and in the top MOSFET, we have the NPN, right? So that's exactly how this junction is the same from the MOSFET versus the BJT. And then from the MOSFET, we still the same. The electron from source will first to inject it to this region and later be swept by the electric field and reach to the drain side. That's how we got the current in the MOSFET. And this is exactly the same. We have the electron inject to the base region and then swept by the electric field and become as a carrier reach to the collector side and become the collector current. So these two operations, at least for me, they are pretty similar, and then so should be easier to understand if you do the side-by-side compare. If you understand MOSFET, should be able to for you, not difficult for you for understand the BJT here. Of course, the only difference is at the MOSFET we apply the gate bias that we can induce inversion electrons. So the width of the base need to be small compared with the minority carrier diffusion length, so because we need to make sure that the minority carrier can be successfully diffused through this base region. Okay, so we will stop here and take a break for 10 minutes because the rest of we will start to describe how we do the step-by-step in the end to derive the equations. Okay, so before we continue, so let's just talk a little bit more about the final exam. So still a little bit update for the course schedule. So today is first day June here. So today we will talk about the bipolar junction transistor. And because we don't have the class, we didn't have class last week, so we will have the one makeup class on this Wednesday at 6 p.m. So because I don't expect that we can finish the bipolar junction transistor today, because otherwise that would be very rushed. So we might still have to use Wednesday time to talk about the BJT, but also if the time is allowed, I would like to introduce some basic related to FinFET, gate all around, and also the CFET on the Wednesday if the time is allowed. And then as a schedule plan already in the beginning of semester, so we should be able to target as a SEM that we will have the next Monday, that we have the final exam from the 10 to 11:30 a.m. So here is some additional reminder that how do we do the grading. So we have the two exams for 75%. That's for the midterm, and final that would be just equally divided by 2. So which means that the midterm will become for 37.5, and then the final will become for 37.5. And then for final, we will do the closed book exam, but you will allowed to bring some additional sheet that you can prepare for the exam. So the reason that normally we do the open book, but I'm welcome everyone to bring all kinds of stuff, but now it's difficult because of the AI tool just way too powerful. So basically whatever the equation can be easily solved for the AI tool. So now we have to change back to the closed book, but you still are able to bring some of the information that can help you for your exam. So we have the 50% for the 15% for the homework, but because due to the time restraint for this semester, so therefore yesterday I already uploaded all the rest of the 3 homework solutions that would be only for you of the self-practice. So we don't consider to do the grading anymore. So in this semester we only have a 5 homework exam for 5 grading homework that will be taken into account as final grading. And we also have the 10% attendance. So as far as I remember, I only probably do like less than 3 times of the attendance check. So I assume that the normally is that if I don't do the attendance check, I assume that everyone is present. But because of this time, the class is pretty flexible. You can attend in the class, or you can watch the video later. So I think it's fine. Just some of the additional bonus for everyone. So I don't do the very serious attendance check. And the last thing is about the final exam. So we will have final exam on the next Monday, and for sure that we will have a final exam on this classroom. But I remember that there's one suggestion from the meeting that because we have the quite amount of students, so normally the space for each one is pretty small. I'm trying to find another classroom, but I'm not sure that I can find it. So we will let you know next week. But anyway, we will still in this classroom as a main location, and we will have the exam that all have the range from the beginning until the BJT, because of the knowledge you need to apply for MOSFET BJT is quite highly associated with some basic fundamental with quantum mechanics, and then also for some excess carrier concentration or PN junction. So I think it's difficult just to devise the range that only after the final, because of in the end, if you can understand the BJT, basically you can understand everything. If you understand the MOSFET, you can understand everything in this class. So then the final exam will cover the completely whole range from the lecture that from the beginning till today till end of the BJT. So we still have the basic question for the homework, and then we will have the closed book, and then you are allowed to bring the 3 A4 page. So that's a total for 6 page for your reference. So my goal is for sure that I don't want to give the difficult time for everyone, but we still need to have a little bit challenging evaluation for everyone, because otherwise everyone will get the same score. So we still cannot make the question very easier, and also the time is limited. Although you can prepare this A4 paper that for your reference, but from the experience that you know from midterm, you should still be very familiar with everything, because otherwise you won't have the time. The time is still limited, so we were still from the 10 to 11:30 a.m. And then you are allowed to bring the handwritten, or if you want to bring the electronics note, that's fine with me. You can print out, but anyhow, it's only limited by the 3 A4, which is 6 page for reference. And then the last thing definitely you need is a calculator. So you need the calculator, which is very important. Okay, so this is information related to the final exam. So let's just start back to the BJT here. So after we understand the mechanism, the next is that we need to start to think about how to derive the equation. So then from the derived equation that we are interested in the calculating currents in the bipolar transistor, and then also similar to the simple PN junction. So the current is mainly determined by minority carriers here. So we have some denotations that the notation is defined on the right hand side, where these are the information you need to know for later that we use to derive for the current equation. So the first of all, in the forward active mode, the BE junction is a forward bias, and then the BC is reverse bias. So this is the minority carrier concentration that we have been plotted in the previous slides, that we have been shown that in these are under the forward bias, these are under the reverse bias, and therefore we have to consider the minority carriers as there are two N regions. This is N region, this is N region. So we have the minority carrier holes so in both the emitter and collector. So we have the minority holes here, and we also have the minority holes here. So therefore, to analyze the current, to calculate current, we will focus on the least minority in this BJT. So for the base region, the steady state excess minority carrier electron concentration is found from the bipolar transport equation. So we can borrow the experience that we learned from the bipolar transport equation, and therefore we have this equation So for this equation where NB is a excess minor carrier electron concentration, and dB and also the tau B are the minority carrier diffusion concentration and lifetime in the base region. So first of all, we look at the excess minor carrier concentration in the base region. And the excess electron concentration in the base region can be calculated as shown here. We have the delta NBX is equal to NBX minus the equilibrium NB0 here. And therefore the general solution from this equation can be shown in here. So where the LB is a minority carrier diffusion length in the base. So that's the first solution that we can got it from the base region. Particularly, we are interested in as excess concentration here. This is excess minority concentration in the base region. And furthermore, we have several consideration here. So we consider that the boundary condition of at x equal to 0 and x equal to xb can be defined as shown here. And then the BE junction is forward bias, so the boundary condition at x equal to 0 is shown at this here. And the BC junction is reverse bias, so the second boundary condition is x equal to xb, which is here. 1 is here for the first boundary condition, and second boundary condition here. So therefore, we have this one here. And then we can use this boundary condition to solve the coefficient of A and B as shown here. And finally, we can get this excess minority carrier distribution in the base region as shown here. Then again, we have the emitter region. So in the emitter region, we are interested in as a minority carrier hole concentration, because that's the minority carriers as a whole here. So we apply the same equation that we have for the base, but now we revise this equation as a holes. So we have a DE So these equations are very similar to the base that we have been used. So therefore, the excess hole concentration as shown here for the emitter region is here. And the same, we got this general solution. We apply the boundary condition at the S prong, and also the X prong equal to XE, which is here, here, and here. So that's our boundary condition. And therefore, we can start to have this solution for the excess hole concentration in the emitter region. So the same analysis can be applied to the collector region as well. So we have the DC. So these are the minority holes in the collector. So with this equation, we are able to solve this minority carrier hole concentration, which consider as a boundary condition at the x prime equal to 0 and x prime here, which is this one, here, and here. So that's our boundary conditions. So finally, we have at least three minority carrier distribution in the base region, in the emitter region, in the collector region. If you really try to plot this equation, that will be exactly the same that where we have been drawn before. This is for the base, so this equation for the base, this is equation for the emitter, and this is equation for the collectors. So one of the very important figure merit for the bipolar transistor is we need to design the current gain, which we have a very similar consideration in the MOSFET. So in the MOSFET, we have this is a typical circuit symbol for the MOSFET, and where we apply the gate bias, and then we will have the drain current. And as you know that in the MOSFET, there's one very important parameter we call the transconductance, GN, which is equal to the derivative of the current versus the derivative of the gate bias. So that's actually can be considered as a current gain, and therefore we will be interested in understand for the current gain in the BJT as we already have for the MOSFET as well. The basic principle operation of bipolar transistor is a control of the collector current by the base and emitter voltage here. So the collect current is a function of a number of majority carrier reach the collector after being injected from emitter cross the base and emitter junction. And therefore we can define what we call as a common base current gain. It's defined as a ratio of the collector current to emitter current here. So if you look at this schematic here, so first of all we will need to pay attention to the three different current components. The first one is a collector current, and then we have the emitter current here. We also have the base current here. So therefore, the common base current gain alpha is defined as collector current over emitter current, which is alpha. That's what we call as a common base current gain. Which is the ratio between this and this. IC over IE is equal to the alpha. And on the other hand, we have another definition, which is a common emitter current gain, which is defined as IC over IB is equal to beta, where we consider as a ratio between collector versus base current. That's a beta is equal to IC over IB. So that's a common emitter current gain. So to understand the current gain is more straightforward to look at this schematic, because if you try to understand the text here, sometimes it's very confused. And then so if you just remember this schematic, that will be highly helpful for you to understand the different definition of the current gain. So the next is that we would like to understand the contributing factors for the current gain here. So therefore we have to a little bit further dive into the different components in there that can all contribute for the current. The first one is that we need to draw as a schematic here, where we have the this is considered as a NPN here, and in between we have the space charge width here and also here, and then we also therefore we have the emitter here, base here, and collector here. So the first one, JNE, the factor JNE is an electron flux that injected from emitter to the base. The JNE is an electron flux injected from emitter to the base, and this is our JNE. The electron flux injected from the emitter to the base. So this is a JNE. As an electron diffuse across the base, a few will recombine with the majority holes here. So once we have electrons injecting to the base and try to across this base, but some of the electron will be recombined with holes, because the majority in the P region is holes. So the majority carrier holes that are lost by recombination must be supplied again from the base terminal. This replacement hole flux is denoted by JRB. So that's a replacement hole flux considered as a JRB here. And the electron flux that are reach the collector is a JNC. So we have the electrons injecting to the base, and then we have this is JRB is here. And then the electrons that reach the collector is a JNC. So this one reach to the collector side. Which is a JNC minus here. The majority carrier holes from the base are injected back into the emitter, result a hole flux denoted as a J plus PE. So the holes from this base region were injected back to the emitter, because this is under the forward bias. So you will have an electron go through from the left to the right, but also you have a holes from the P to the N as well. And this contributing factor that we call as a JPE plus. So we also have this one called JPE plus. Some electron holes are injected to the forward bias BE space charge region, will recombine in this region. This recombination leads to the electron flux as a JR minus. Where is this? It's a JR minus. And furthermore, the generation of electron and holes occurs in the reverse bias BC junction, because this junction is under the reverse bias. And if you still remember that what we have been talking about under the reverse bias, that there is a chance to have the electron and hole generation under the reverse bias, and therefore this generation yields the whole flux of a JG plus here, which is shown here. We have a whole generation JG plus here. Finally, the ideal reverse saturation current in the BC junction is denoted by JPC 0. So these are the overall current contributing factors that we consider, that we have the forward bias between the emitter and base, and then reverse bias between the base and then the collector. So here is some more details from this graph. This is a schematic that is more in a more comprehensive way, but it's exactly the same that where we have been drawn in the last slide. And this is a detail of the explanation for each contributing factors here. Finally, this is more important, because right now we want to understand how to derive the common current gain here. So we have the alpha 0, where we have been defined as a IC over IE. So therefore, the current ratio can be also considered as a delta IC versus a delta IE. Now we have to think about which component in the end cause the IC and IE. So the first one, the collector current will be equal to the JNC as shown me here. So this will become the JNC. But the emitter current here, the current reach to the emitter side. Now we have to consider the JNE is here plus the JR plus the JPE here. These are all the current will reach to the emitter side. So that's the first step. Now we try to play as a little bit trick to further divide this equation as a 3-term. So now we revise this as shown here. The first term is JNE over JNE plus JPE. I will explain why we will do this later. So the second term, the JNC over JNE. And then the third term, the JNE plus JPE. Over the JNE plus JR plus JPE. So we divide this as here. But first of all, let's look at how we can do this. This is just a mathematical trick because you look at this equation in detail, then this and this will be removed, and this and this will be removed, right? So you have this and this removed, and this and this removed. So this equation is basically the same as above. So that's why from mathematical point of view we can do this. Try to consider 1 divided by 3 terms. But next is we will be more interested in that what is the physical meaning for each one. So we define this as a 3-1 called the gamma, alpha, and eta here. So the first one, the gamma factor here, which is this one, the JNE over the JNE plus JPE. So now try to look at the schematic here. Here is a JNE, and where is the JPE? Here is a JPE. So basically, this is a term to describe that the electron from the emitter to base over the total carriers in here. The total carriers, you need to consider electron holes. So we consider the electron injected over the electrons plus the holes here. So therefore, we consider this as what we call as a emitter injection efficiency. Because we are interested in as a gamma equal to amount of electron can reach over the total, which is electrons plus the holes. So the ratio between this and this plus this. So that's why we make it the first term, because we want to decouple the part related to the emitter. So that's we call this as an emitter injection efficiency. The next one, alpha T, where we define as JNC over JNE. So where is the JNC? Here is a JNC, and here is a, where is the JN? Here is a JNE here. So we consider as a alpha T is a JNC over JNE. So this term is trying to understand initial you have amount of electron being injected to the base, that's we call the JNE, and then the amount of electron being injected and reached to the collector. So we are interested in this one over this one, which means that we are interested in understanding that the transport in the base region. So that's why we call this as a base transport factor. So last one, which is this one, is equal to the JNE plus JPE over JNE plus JR plus JPE. So this is a term that we are interested in. That where is the JR? This is JR. So this is a term to describe that you have the total JNE plus JPE, but now we also consider that the ratio between the overall we is considering as a recombination. So therefore we call this as a recombination factor. We are interested in that how much the recombination is contributing. So therefore we call this as a recombination factor. So that's why we spend the efforts try to analyze each contributing factor. I can fully understand that the previous slide we talked about this contributing factor is not very straightforward, because of, to be honest, if a textbook didn't mention like this, probably we will never be able to understand there's the contributing with such detail. But just try to think about this and try to force yourself to understand that it's indeed that we have this contributing factor, but then the purpose for this contributing factor is allow us in the end we can analyze this current gain from the one general equation divided by 3 terms, because this general equation doesn't give us a very meaningful physics, because this is an overall contributing result, but we are more interested in how each region might influence the current gain, and therefore we divide this. We consider some mathematical trees as a 3 terms here, and then if we consider these 3 terms, then we will get a much more physical sense of each one term. For example, the first one we consider as an emitter injection efficiency. The second one is a base transport factor. Then the third one is a recombination factor. So with these 3 terms, finally we are able to analyze further that how each region design could in the end to influence the current gain. So here is some more details that the calculation for the emitter injection efficiency. So we're starting from this one, and then we can do some mathematical tricks here, and we try to estimate the JPE, JNE from this equation, and in the end we get this one, and finally we got this one. So now we can start to correlate this emitter injection efficiency with the design of the base and emitter region. So now you see the different base doping, emitter doping, base width, emitter width might in the end influence our emitter injection efficiency. This is our goal, because we want to make this factor can be correlated to our design, because so far we don't know that what would be the concentration impact, what would be the width of the emitter base collector will impact our current gain, but we want to make this have a certain correlation. So now finally we have this gamma is correlated with NB, NE, XB, XE, because consider as a semiconductor device engineer, in the end we want to design our transistor. Now these factors can be designed by consider the different these parameters. So that's why we spend the efforts here. And similarly, if we try to further to estimate the base transport factor here with this all the calculation, in the end we got this one, the alpha t is equal to 1 over cosine, hyperbolic cosine xb over lb. And also the purpose is we want to know the alpha t is correlated with xb lb. Sorry, I should not use this. This is not a proportional. It's just as a function of xb lb. And also this one, this is not a proportional. It's just a function So now we know that the XB and LB will highly influence the base transport factor. But if you think about this again, you will feel like this is really makes sense, because what does mean the base transport? We are interested in the base will influence how the current flow, and in the end the base transport factor will be highly depends on the XB, which is the base width, right? So that's pretty makes sense. And then the LB, that's the diffusion length, so which also pretty makes sense here. So the last one is a recombination factor here. Also, with all this calculation here, finally we get this term. So now we can understand that the recombination is factor which is correlated, is a function of the base and emitter voltage, which also pretty makes sense, because the we have this is under the forward bias, right? So you have the electrons from the emitter to base, you have a hole from the base to emitter, and somehow recombination can be happen here. That for sure will related to your bias applied, because your bias VB will determine that how much your electron from emitter to base, how much of a hole from the base to emitter. Although the calculation, the derive this equation is somehow it's not very straightforward, but I believe that in the end the equation we got here is it's a simplify, and then it's easy to understand. So finally, this is a summary. So now we have to consider again this schematic, where there are three most important current here. First one is collector, second one is base, and we also have a one as a emitter current. And from this simple circuit networks, we can understand emitter current is equal to base plus the collector current. So therefore, the emitter current is equal to base plus the collector current here. So with this one, we can get this formula, all divided by IC collector current, then you can get this one. And therefore, this will be equal to 1 over alpha. Just look at the definition of alpha, you will find it. And this will be equal to 1 over the beta. So therefore, we have the equation can allow us to calculate the alpha and beta. So therefore, the alpha, the beta is equal to here. Is equal to alpha over 1 minus alpha. And then the alpha is equal to beta over 1 plus beta. If you have followed the electronics in the undergraduate class, this is the equation that we have seen in the basic electronics when we talk about the BJT circuit. This is simple, but it's very important for when if you need to analyze the BJT circuit, you definitely know that this beta and alpha correlation. But now here we derive again. So this is a summary that where we have been derived. We have this equation, this equation, and in the end, we put all these together, we get this alpha is equal to this term, and beta is equal to this term. So this gives us a kind of the design strategy that if we want to increase the beta, if we want to make the beta as larger as possible, then what should we do is to make the base width smaller and increase the emitter concentration. So therefore, overall, as I always say, that although many of you might request that I should put more effort to derive the equation, but for my understanding, for my personal experience, I think equation just a tool. It's more important to understand how we use the equation, what's the physics behind. So in the end, all these very complicated calculations give us a very simple strategy how to increase the current gain. Is either we increase the emitter concentration, and second, we make the base width smaller, so that's a decrease base width. So that's how we can make our BJT has a very good current gain here. So that's why we spend this effort, this equation. If you really try to derive this equation, that would take like 1 hour, because those equations, some you see the hyperbolic, like a sine, cosine, this is not easy to be solved. But anyhow, in the end, we got a very simple conclusion that we need to increase the concentration or we need to decrease the base width. But now you get this conclusion, you back again to look at this graph, then you can get quite a nice sense that why we have to decrease the base width. If we can make this base width smaller, then we can getting more and more current go through, right? So I think that's also pretty straightforward. If we can have the concentration in this region higher, for sure that we will have more electron being injected, right? So that's also, if you look back that how this equation try to tell us, and then you try to rethink about this schematic, I think all the conclusions are very straightforward. We want to have a higher concentration in the emitter. That's how we can get more electron being flowed. And then we want to get the base smaller, because we want to make sure that more electron can reach to the collector. And therefore, if you back to the beginning, when we first start to draw the carrier concentration in the BJT, why we make this as a N++? Why we make this N++? Because we want to have the good current gain. That's why in the beginning we already consider this. Of course, in the beginning we don't talk about it because that's way too complicated. But in the end, you can realize that the reason choose the N++ here has a reason. The reason is because we want to have a higher current gain. Okay, so we will stop here because the rest is a non-ideal effect, and then we will leave that for the Wednesday class to finish BJT, and so we will see each other on Wednesday. Okay.